All right. Many thanks. First, many thanks to the organizers for the invitation to speak here. Today, I'm going to talk about some update with works with my collaborators on the subject of probing high energy physics using primordial density perturbations in the primordial universe. And I will also spend some time um, reviewing the big picture, overall big picture, in case the audience is not familiar with the subject. So here's the outline of the talk, which also more or less the conclusions. First, I will first point out that during the primordial universe, such as the inflationary epoch, all particles with mass up to the Hubble parameters or even higher can be excited, are excited quantum mechanically and can be excited classically. So I will discuss how these particles leave their imprints in the primordial density perturbations as features and non-Gaussianities. Some of them may be probed by astrophysics observations of a larger scale structure today. And I will discuss how the signatures are, including the particle mass and the spectrums, and also the scale factor evolution, A of t, of the primordial universe, the background universe. Especially the latter information provide a alternative direct evidence for the inflation or a alternative scenarios. In the last part of talk, I'll update with an example that we recently constructed. It's an inflationary primordial feature model that can explain both the large and small scale feature anomalies, statistically marginal feature anomalies that is present in the current CMB measurement. This model will reveal a clip of interesting history of our universe during its primordial epoch and realizing some of the properties I outlined above. And we show how to test these kind of models in future experiments. Okay, so let's start with inflation. And we all know it's a leading candidate for the origin of the Big Bang. And during inflation, quantum fluctuations of fields start out with a very small wavelength, gets stretched out at the superhorizon scale, and with the subsequent Big Bang phase, become cosmological scales. So these fluctuations are called the density perturbations. And the relation between the quantum fluctuations and these density perturbations is the key that we are able to study the fundamental physics during the primordial universe using today's astrophysical observations. So during inflation, the energy scale of the universe is very high, given by Hubble parameters. We don't know how high it is. It has an upper bound of 10 to the 14 GeV. So what can we learn about fundamental physics at this energy scale? So the tools that we'll be using are the correlation functions of the density perturbations. Basically, they are related to correlation functions for the quantum fluctuations during primordial epoch. And those density perturbations are the perturbation maps of, for example, CMB anisotropies or galaxy distributions. And the correlation functions we use are power spectrum, 2-point correlation function, and non-Gaussianities, such as 3-point functions, which we usually call bispectrum, and 4-point trispectrum, etc. So there are roughly two kinds of properties that we can study based on what kind of correlation functions that we study. So the first is the scale dependence, namely we rescale all the momentums in a correlation functions momentum. And second is shape dependence, in which that only appear in non-Gaussianities, in which we can study the dependence of correlation functions when we vary the shape of the triangle. We will first study the non-Gaussianities first. So the physical question we are going to ask is, what are the signatures of particles that are created on shell at the energy of h in these correlation functions? And we will also ask the questions how to distinguish inflation from a possible alternative scenarios in a model independent fashion. Okay, so first, the particle spectrums in the inflation background. So the minimum particles that we want for inflation model is, of course, single field infotons. So it has a very small mass. But in a UV completion point of view, there must be a lot of particles, which is very heavy, at least a lot of particles much heavier than the Hubble parameters. But we also know if you have a lot of light scalar particles, those particles will receive mass of order h from quantum loop corrections or from coupling to the background. So in fact, this is a famous eta problem, is how to get actually the light fields to satisfy the slow roll conditions so that inflation will happen at all from the tunings of this order of h, a lot of mass of order h particles. So the natural picture of a particle spectrum in an inflation model would be you tune the field such as that one field may become very light, and there are a lot of particles of order with mass of order h and even higher. So the particles which has a mass of order h is particularly interesting because they may not be important classically, but they will play important role, can be very important quantum mechanically in terms of leaving their signatures in the density perturbations. So this kind of inflation models we call it quasi-single field, in distinguished from to be distinguished from the single field inflation model. But those particles which has with mass up to order h that are produced during the inflation can couple to the infoton and then later decay into the infotons and measured by the density perturbations in terms of study of correlation functions. So what are the signature of them in terms of correlation functions? To study that, we will look at, for example, the vortex such as this, which couple to infoton and the massive field. And we take a special limit, which turns out to be the limit where the signature is most clear, namely the squeeze limit or the soft momentum limit, in which the wavelength of the massive particles is very long. So the momentum is small. So in a long wavelength limit, the massive field behaves actually classical-like. So it oscillates as a harmonic oscillators in a real-time t, and with an amplitude decay as 1 over a to the 3/2. Basically, they are diluted by the expansion, for example. So those harmonic oscillations will serve as a background clock for the shorter wavelength infoton field. So now we have two kinds of oscillations. One is the clock oscillations from the massive field, and another is the subhorizon oscillations of the infoton field itself. So these two oscillations has a very different kind of frequency dependent. One has a fixed frequency determined by mass of particle in the real time. Another is a harmonic oscillation in the conformal time. So its frequency is changing in the real time. The conformal time and the real time is related by the scale factor. So if you have two frequencies, one fixed, another changing, you will have a resonance at some point, mode by mode, given by for each k values, and you will get some dependence on k, which look like a momentum to some power, which is given in a large mass limit, which is given by this imagined number. And we also know the momentum has to appear in terms of ratio because quantum fluctuation does not break the scale invariance. So you have to have these ratios, which is invariant under the scalings, k long over k short. Also, if the massive field, intermediate massive field has a spin s, and if we try to work out its projections at an angle theta, namely by looking at the configurations where the infoton span an angle theta with this long wavelength modes, we will have an angular dependence as a function of spin s in terms of a Legendre polynomial. So to summarize, if you do a more concrete calculations, basically you will get the result that I qualitatively illustrated previously, namely the mass of and the spin spectrum of these intermediate massive states are all encoded in the soft limits of non-Gaussianities. For example, for the 3-point correlation functions, it is in a squeeze limit, in which if you take the squeeze limit, you will get a K ratio dependence, where now I put in M in arbitrary value, not necessarily larger than H. So you have this power where the power measures the mass spectrum of particles. Notice that in a large mass limit, you will have oscillatory dependence of this K ratio because you have an imaginary number here. But if you have a mass less than 3/2 H, the mu will be imaginary. So you still get a non-analytical scaling of the momentum, which is also a signature of the massive field. So both behavior are non-analytical in terms of K. If you study its angular dependence, you will have the spin information. And in front of that, you will also have a Boltzmann suppression, which means if you want to excite a particle which has mass much larger than H, you will get penalized by something like a thermal effect. So this has been called the cosmological collider physics because it has a close analogy of how to measure the particle spectrums in terrestrial colliders. On the other hand, I have shown you the pattern of these signals. There's also a very important overall amplitude of these signals. It can be large, it can be small. It's a very model-dependent thing. In many cases, they're very small, as expected, but in some cases, you will get large signals, which will be predictions. So for example, if you have a UV complete model of inflation, and you can work out the predictions, the consequences of your particle spectrum predicted in your model, and see if you can have some measurable predictions. So there are many extensions and applications of these programs. People have been using this, trying to see if there can be any minimum signatures of standard model by coupling the standard model to infotons to study the implications for the supersymmetry fine-tuning problems and generalizing it to a more general EFT and strong coupling case, and working out signatures of, for example, stereo neutrino gauge bosons, ground unifications, and higher spin fields, and applying to some other cosmological setups such as curvaton scenarios. Okay, so the next part of talk, I'll talk about the imprints of those massive fields in the scale dependence of density perturbations. Remember previously, I talked about the shape dependence. The scale dependence has a nice aspect because you can observe it even in power spectrum. So those signals will appear as so-called primordial feature signals. Those signals are strongly scale-dependent deviations, typically oscillatory from otherwise scale invariant spectrum. So there are many ways and aspects these features can be observed in the primordial spectrum. For example, if you add some steps or bumps in your potentials, you will break the scale invariance temporarily and see signatures in the primordial power spectrum. But here we'll focus on two fundamental questions. The first is, can we distinguish inflation scenario and the possible alternative scenarios in a model-independent fashion? And second, we will construct explicit models, which has some motivation from data that tells you some very interesting evolutionary history of the cosmic inflation. Okay, so first, very brief motivations of comparing inflation and alternative to inflation. Now, we all know inflation is the leading candidate theory for the Big Bang model, but we are still not sure and searching for direct evidence for inflation experimentally. And there are also a lot of efforts trying to build alternative scenarios to inflation, and they typically face more theoretical problems than inflation. But at least for me, the essence of those model buildings has told us something useful, namely some toy models of alternatives to inflation act as a reminder that several key predictions of inflation may not be unique to inflation scenarios, and there may be alternatives to inflation that should be explored and tested. So to give this will be a very extensive topic. Obviously, I'm not going to going over that in any details, but I just give you one examples of this kind of properties, the superhorizon perturbations. Now, so for inflation, superhorizon perturbation is very natural, but also being realized if you don't have an inflation background, for example, you have a contraction background, well, naively, you don't get superhorizon perturbations because the scale factor is shrinking. So the wavelength of quantum fluctuation also shrinking. But in some contraction background, the horizon of the universe is also shrinking and in a speed faster than the scale factors. So you end up with the following pictures with the superhorizon perturbations anyhow. And these two actually are equivalent up to rescaling. Okay, so it will be nice, for example, if we can have some observables that can directly measure A of t. That will solve the problems because A of t, namely a scale factor of primordial universe as a function of time, is a definition of any scenarios. And can we do that? So in order to motivate this, let's first look at how we build models of inflation or alternative to inflation. So we look at the landscape of potential. Here's an example of landscape in 2 dimensions. In the real UV complete theory of the inflation model building, we will have much more than 2, tens or hundreds, if not more, dimensions. And the infraton trajectory is determined by the low energy value in this potential landscape. So because of complications, it's natural to expect that the low energy trajectories of the infraton or some other alternative to inflation scenarios may not be smooth. It can turn or it can encounter to some obstacles, namely we call this sharp features, and in the orthogonal direction to the valleys, there are potentials that lift. Basically, those directions are the massive fields that are perpendicular to the low energy trajectories. So now we can envision the following pictures in which the inflation undergoes 2 different stages. The first, you have stage 1. At the end of it, it encounters some sharp features, which may be a turning or falling interactions, which displace the infraton temporarily from its eventual attractor solutions. And if the orthogonal direction, the potential in the orthogonal direction is high enough, namely the mass of particles is large enough, it will trigger an oscillation of massive field and start a classical oscillations. Now, these oscillations proceed in a very standard way if the mass is high enough. Namely, the mass is higher than the event horizon scale of the primordial epoch. They will oscillate harmonically. So these oscillations actually, as I will show, will provide a ticks as a time coordinates t. That induces ticks in the density perturbations as features, which we call the clock signals, that directly encodes the information of A of t. We call this primordial standard clocks.
5 minutes. I know you started late, so 5 minutes left.
Okay, thank you. So the way the clock signal is generated is very similar to the previous examples that I showed, but you have 2 oscillations, but now we just promote the exponential expansion by a general scale factors. So when you do integrations, you try to, those oscillations try to cancel until you reach a resonance point, and you figure out the resonance point and plug back in, and you will get a phase written in this form. Notice the t of k and tau of k are the inverse function of scale factor dependence on t and taus. Okay, so now you see the phase of these oscillations as a function of scale directly encodes the scale factor A of t in terms of inverse function. Okay, to give a very rough sketch of the overall picture, there are two types. Remember, we have two types of features: sharp feature and resonance features. The sharp features is very easy to work out. It's just sinusoidal function of k, and because the sharp feature is roughly a delta function in terms of t. So this kind of sinusoidal runnings is a signature of sharp features, but they are not signatures of any massive field, nor does it record A of t. It's universal for all scenarios, but it's an important signal as a part of full signal. The second part is more important for this purpose because as we have explained, they will encode A of t informations. So they take the following form. Now let's ignore all these numbers, which are all constant. Ki is also constant, and concentrate on the phase dependence on k. And here we have taken a explicit example of power law, where we promote p to be arbitrary numbers. If p is larger than 1, it's inflation. Otherwise, it's non-inflation. So we see the k dependence is actually the inverse function of A of t. So that's an example how A of t is measured. And in terms of sketch, and you can see if you trying to look at the predictions on the power spectrums, you will get roughly the following pictures, which has differences between different scenarios. First, the green signal is the sharp features, which are all look same, but the clock signal are all different. Depends on what kind of background you have. For example, the inflation scenarios, expanding scenarios, the wavelength increases as a function of k, while the contraction scenarios decreases. Here I talk about classical oscillations. In fact, there are some interesting connections with the quantum oscillations that I explained previously in cosmological collider physics. To explain that, let's just look at the large mass limit, in which the non-Gaussian dependence we see of this form, and in this limit mu is imaginary, so you get sine mu log k. In retrospect, the reason we got log is because we have assumed the inflation. So the cosmological collider physics is not only measured particle spectrums, but also the scale factor evolution of the inflation. Okay, so in the last maybe 2 minutes, let's look at explicit constructions of this primordial standard clock model with data comparisons. So on the left side is the famous CMB spectrum standard model, and we are interested in deviations. So we subtract off the standard model and look at its residue, so-called residues. Here is a TT residues, but they also have a counterpart in TE and EE. So you notice there are some marginally interesting deviations, statistically consistent with the standard model, but we will use it as a hint to do some interesting exercises. Now notice you have some large-scale anomalies and also small-scale anomalies, and these well-separated features may be connected by the standard clock effects that we have discussed previously. So skipping the motivations of how to get these models, let's look at the actual models that we have here. So here is a bird's eye view of potentials. The Lagrangian, you can ignore that because it's being pictured here. So we have two stages of inflations, first rolling on top of potentials, and then the inflaton encounters a cliff and rolling down and become a fast slow model until it enters a curved path. It overshoots the bottom of the valley, climb onto the side of cliff, and excite a classical oscillations, which is very small here, but you can see the blow up in the inset. And then in the last part of the evolution, the oscillations decays because of the Hubble frictions and settle down to the second stage of inflation. The last stage is very model independent. So that's what we use to measure A of t. But the first part, all this, are very model dependent because they are sharp feature signals. But it's also nice because if we have clear data, that can be used to reconstruct a very detailed picture of inflationary history. So we work out the power spectrum in the left and compare to with data of Planck 18. And you can see the promised fit in the large scales and the fit in the small scales. You can also see some correlated fit in the polarizations, although the error bar polarizations is very large so far. And also there's a separation of sharp feature and the clock signal.
So we do need to wrap up soon. So
okay, yes, and this best fit is currently indistinguished from a standard model because the Bayes vector is around 0. Although, despite the fact that we have introduced 6 parameters, and you can see a clear small bump of indication that the massive field has a mass of 18 times h. Okay, so in maybe last 30 seconds, I'll just quickly go over how this might be improved by future experiments. I'll talk about 3 experiments. And basically, the first experiment, the light birds, they are both measuring the polarizations. The light birds will be very good at large scales, as you can see from the error bars. And here, the error bar is so small that you can even not see that in contrast to the Planck scale, or in the Planck satellite. The second experiment, which is Simon observatory, will be very nice in the short scales with a very small error bar. So they will probe the clock signal that has information of AOT. And the last is currently is not funded, but it's a NASA-funded mission study. If it be launched, it's a satellite experiment that will be measuring the polarizations in all scales, very close to cosmic variance. So that will give us a very complete picture of if this signal is there or rule out this signal. And also, I just mentioned that the correlated signals can also appear in galaxy surveys and the 21 centimeter from hydrogen atoms. Interested readers you can look at those references. And I will just leave the conclusion here, basically the same as I summarized at the beginning. Thank you very much.
Okay, thank you. I'd encourage people to use the chat or Slack function. But if there's a question that in the gallery, you can take it now. Otherwise, we can. I'm scrolling through. I'm not seeing one right now. So I'd like to thank you again for the talk, and